Chapter 3 is all about functions. You've almost definitely heard functions before if you are watching this video as it pertains to math, and I probably don't have to emphasize to you how important and fundamental functions are for basically any kind of math we do in the real world. And in chapter 3, we're going to first talk about the concept of a function, and that's going to include like what qualifies as a function. We're going to talk about the notation we use. We're going to talk about limitations to a function, like domain restrictions, and also we're going to talk about the idea of range. We will look in depth at linear functions and quadratic functions. The most important thing we're probably going to do in this chapter is discuss the idea of transformations of functions, or how to graph things really quickly. We will talk about operations on functions, addition, subtraction, multiplication, division, and also composition of functions, and be mindful of domain and range throughout that entire discussion. And then we will also talk about direct and inverse variation, and lastly, a very important extension into calculus, which is a pre-calculus class after all, something called a difference quotient, which is really just the composition of functions, and this idea that you can find a thing by like using kind of substitution. Anyway, we'll get into that much later in this series of videos, but the first one is about the concept of a function. So what is a function? A function is it's a mathematical relationship. A relationship in math describes how inputs and outputs are connected. And we can represent relationships in a bunch of different ways. And here's some of the common ways. So you see, like, there's nothing crazy here. These are the color, besides the colors, of course. But what we have here is just different ways to represent the same data. So you can see that, for example, 0 is paired with 3, 1 is paired with 5, 2 is paired with 7, and 3 is paired with 3. And we have that represented here in like a T-chart. We then have them graphed as ordered pairs and then listed out as ordered pairs. And so how do we determine, like, based on this data, like if it's a special kind of relation called a function or not? Well, a function is a relation that pairs each input with exactly one output. For example, for each person in a class, there is one assigned seat. For each book in the library, there is a locator number, like a Dewey Decimal System thing. For each book in the library, I already said that. For each book in the library, there's a number of pages in that book. And importantly, another way to think about this is that functions are predictable. If you plug one thing in, you know that you're only going to be able to get one specific thing out. Think about things in the real world that are not functions. I'll tell you one right now, like Chipotle, right? If you eat Chipotle, you might have a normal morning afterwards, or you might not. And I think you know what I mean by that, but the fact remains that eating Chipotle is not a function because it's not predictable how your stomach is going to feel the next morning. And there's all sorts of examples of this. If you think about, like, I don't know, like anything that you're taking a chance on, like you're rolling a dice or something. Like, you don't know, you're gonna roll the dice, but you don't know if you're gonna get a 6. You might get anywhere between a 1. That's not a function. So functions are predictable. And so let's see, is this here a function or not? Now remember what a function is. Every input has only one output. So here 1 gives me 6, -5 gives me 5, 1 gives me 4, and -2 gives me 3. So right here you can see that this is going to be not a function, because if I plugged 1 in, an x value, I might get either a 4 or a 6 out. That means this is not a function, right? That is a textbook definition of a non-function. Okay, what about this one? So we have 6 is paired with -4, 19 is paired with 8, 7 is paired with -4, 3 is paired with 6. You might at first glance think that this is not a function because you see the two -4s in the outputs, but this is totally fine because it's not that a single input is giving me two different outputs. It's that two different inputs are giving me the same output, which is completely fine. Think about something that we know to be a function that's like a sine function, right? It looks something like this and keeps going on and on and on forever and ever in both directions. If I said, and if I get, if like this is not a good example. Oh yeah, it is. If I gave an input of like pi over 2 and 3 pi over 2, they're both going to give me an output of 1, right? But this is still a function, right? There's no, I can't, if I plugged in like this, I'd only get one answer out. I'm not getting some other answer out. So this is a function. Okay, how about this one? 1 gives me 6 and 5 gives me 6, -3 gives me 2. This is a function. It's okay, only there's only a specific, each input just has a single output. And then lastly, here's just a graph, right? Is this a function or not? So the easy way to check, again, is let's say I plugged in 3. If I plug in 3, well, I'm going to have a y value looks like 0 and a y value of 4. This is not a function because my single input of 3 gave me a y value output of either 0 or 4. And that will apply for basically anything within the domain of this. This is called an ellipse. And this gives you a chance to illustrate another property. It's the same idea, it's the same property, it's just shown differently, of a function, is that if it were a graph, it would need to pass what's called the vertical line test. So imagine that this red line represents an input. If I drag this red line across the breadth of the domain of the function and it intersects the graph more than once at any of those points, then we have a non-function. We don't know what output will come out if we plug in a certain input. So the vertical line test is simply testing to see if every individual input has a unique output. Oh, that's not right. Sorry, if every input has just one output. Okay. So another thing about functions is this is the notation that we see all the time in math, f of x. And usually when we're talking about f of x, we're talking about an x or y coordinate plane where y is a function of x and we just say y equals f of x. So instead of saying like f of x is equal to 3x plus 2, a lot of times you'll just see y equals 3x plus 2. This is still a function. It's a linear function. It's a slope. It's a line with a slope of 3 and a y-intercept of positive 2. But these are, for the most part, they're interchangeable. Now, it's important to note you won't always see a function as f of x. You might see it as like area as a function of width or something like that, or profit as a function of sales, or like just different ways of describing this based on the context of the problem. But if we're just doing purely mathematical things on a coordinate plane, f of x is usually the way you'll see it. Or if you're given multiple functions in a single like problem or discussion, you might see f of x and like g of x. But if x is your input, we're probably talking about a coordinate plane, so you could easily just sub y in for these things. Now, what does this say right here? Well, this thing inside the parentheses is your input. So for this one, x values are inputs. For this, width values, like values for the width of something, of a shape. This is like the number of sales as profit as a function of sales. And then f is like shorthand for all the things that are going to happen to that x value when you plug it in, and then whatever this equals at the end is your output. Okay, so f of x is an output. It's functional. This is called function notation. All right, let's examine this a little bit more. So here I have f of x. Now, in this specific function, what's happening to x? It's being multiplied by 3, and then after that we're adding 5 to whatever the product of the input x and 3 is. Okay, so 3 is happening to the input, x is happening to the output, sorry, 5 is happening, multiplied by 3 is happening to the input, then after that we're adding 5. And you could just plug numbers in here, right? X, this is saying what is f of 3? Well, I'm just going to plug in 3 for x, like that 3 right there, bam, plus 5. So this is some number, 14. I can do math. This one, if I have -2, f of -2 is equal to 3 times -2 plus 5. This is equal to -1. F of 8 is equal to 3 times 8 plus 5. This couldn't be more straightforward. I hope you'll agree. Okay. Now what if we have something like this? Okay, so again, all we're going to be doing is plugging in different values in for x. So f of 4. We've got 5, and you can do this, you can pause the video and fast forward it to not hear my annoying voice. So 5 times the square root of 0, which is 0 plus 2, so this is just 2. F of 20 is 5 times 20 minus 4 plus 2. So 5 times the square root is 16 plus 2, 5. So 5 times 4 plus 2. So 20 plus 2 is 22. Okay. Let's see what else we've got. Now notice, notice one thing, right? And this is, you might be like, wait, how come you didn't put plus or minus 4 right here? That's because when you see this in a problem like the square root of 25, if you're like, what is 6 times the square root of 25? This is always 30. It's always 30 because this square root of 25, you're not talking about x. You're not talking about this being some number squared. You're not talking about it being x squared. You're just asking what is the square root of 25. It's called a principal square root. It's just 5. It's always positive 5. Okay, so anyway, just that's an unrelated side note. But anyway, 22 is the answer to that one. This last one, f of 9 is 5 times the square root of 9 minus 4 plus 2. So this is equal to 5 root 5 plus 2. And that's it. Like, you can't simplify this, unfortunately, any more than that. So that's it. You just plug numbers in. That's it, called evaluating a function at a certain input value. Okay. Okay, now we get into an important idea, the idea of domain and range. Every function has a domain and range, and it's not going to be that important right now, but much later on as we progress through this course, we're really going to need to be considering the domain and the range of different functions. And I'll tell you right now, just I'll give you a heads up, and we're going to talk about them individually, but the domain of a function is always easy to find. The range is not always easy to find. Sometimes it is, but if you think about all the possible math problems you can have, the range is very difficult to find a lot of times. So let's think about what the domain and the range are in case you don't know what those are. So for this, what you can think of as a domain, somebody described this to me once. It's all the x values that are legit for a function. So any x value that I can plug in without there being some kind of mess up is fine. So for a line, it's going to be any number. What does that mean? Well, like let's say this line graphs something like this. Oop, that is not a good color. Let's say this line graphs something like this. Okay, if I had a giant flashlight and it was above the x-axis, like infinitely high above the x-axis, and it was shining down on the x-axis, imagine the line would like cast this shadow on the top of the x-axis right here, and I had another light at the bottom shining up. It would cast a shadow on this part of the x-axis. But basically, there's no value for x that you can't plug in here that would give you some output value for y. And so that means that the domain of a line, not any line, but most lines, is all real numbers. Okay, so you can say it's you can represent that as the domain is a set of all x values such that x is an element of the real numbers. You could say it's just all real numbers. It kind of depends. Like there's lots of different ways to represent range, and we'll talk about it in a second. The one that you will see and we will use a lot in this class is in interval notation. Negative infinity to infinity are all the values that are possible for x. So again, here's the different ways you can represent domain. You can use set notation, so that'd be all real numbers. This is the same thing in interval notation, or just something basic where x can be all real numbers. Now, again, listen to your teacher about how they want you to describe this, but just be comfortable where you see your different representation here and you know what that means, so you can kind of interpret between them. Now the range of a function, whereas the domain were all the x values that are legit, the range are all the y values that are legit. So y values that are legit from the inputs. So if you plug in all the values from the domain, the range is a set of all the y values or the outputs that can come out from those inputs. You can again think of it kind of like a shadow. I don't know if this is helpful. It could be a complete waste of my time, but the graph of this f of x equals x squared, it looks something like this. Okay, if you don't know that yet, don't worry. and you shine a light from the right side and the left side, like where's the shadow on the y-axis? It's here and here, right? Not anywhere down here. So the range of this is everything that's positive. So y is greater than or equal to 0. You can say it's like again, his numbers greater than or equal to 0. There's multiple ways to represent the range, and they are like this. So set notation again, you can use interval notation. This is going to be the one we tend to use mostly in this class, or just a really simple statement, an inequality that represents the part of the y-axis that is like shaded. Now, you will find that the range is actually, it's a simple concept, but getting the range can be very difficult, and it requires some kind of really like thinking about things in a different way. And you can like there's all sorts of tricks, but if you have the graph of a function, it's like immediately easy to find a range because it's just the y values that are legit, right? You can read it right off the graph. So you'll find as we move through pre-calculus that you will probably graph things before you find the range, just because it makes it so much easier. The domain, again, though, is always easy. So here is what's called a discrete function. Now this is not continuous. The dots are the only thing on this function. There's no line connecting them. So if I wanted to find these values, let's say I wanted to find g of 1, well 1 is my input, and so g of 1 would be 2. If I wanted to know, if say g of x is 3, I want x. Well, I know that g of x, this y value, g of x, the y value of 3 is right here, right? So that means that the x value that gave me that y value of 3 is 4. If a g, again, is similar thinking, right? 1 is 1 is right here and 1 is right here for g of x. That means that this could x could equal -1, or x could equal 3. No, that'd be solving for x there. What is the domain of g of x? Again, those are just the x values that are legit. So literally, it's -1, and we're reading from left to right, 0, 2, 3, 4. That would be the most concise way to represent the domain. Or sorry, not 0, 1. Like that, -1, 1, 2, 3, 4. And then what would the range be? Well, we're going to read the range from bottom to top. So we'll say that the range is a set of all y values such that y is equal to, again, you could have done that for the x values too, the set of all x values such that x is equal to those numbers, set of all y values such that y is equal to -2, 1, and we don't count 1 again because it's already accounted for, 2, and 3. So that's the range of that. All right, let's look at domain restrictions. Now, you have been told throughout your math career that there are 2 things you can't do in math. And if I gave you time, and hopefully everybody watching this video will be able to answer. If I said, what are the 2 things you can't do in math, you'd be able to get them right away. Well, with a little bit of time anyway. And they are, you can't take the square root of a negative number, and you can't divide by 0. And that's it, okay? Those are the 2 instances where you will have problems with the domain of a function. Always. That's the only time we're going to have these issues, okay? You're either taking the square root of a negative number or you're dividing by 0. So what does that mean? It means that for g of x, right, the domain of g of x, x plus 3 must be greater than 0. Because I need it to be positive. It can also be 0, so it can be greater than or equal to 0. So I need to just solve this inequality, and I'll have the domain of g of x. So x is greater than or equal to -3. Anything for x that is greater than or equal to -3, so -3 on, is going to be legit. So how do I say that in interval notation? Just like this. Okay, that's the domain. Or if I was using set notation, the set of all x values such that x is greater than or equal to -3. Okay, so that's how you find the domain of something that has a radical, a square root in it. Now, what about when you have a denominator? Well, this is again, x needs to be, it's anything that is not these numbers. So let's think about what that means. Anything that doesn't make the the denominator 0. Okay, the denominator of this is x squared plus 6x plus 5, and that is a quadratic, which we can factor to x plus 5 times x plus 1 Okay, and so we know that x plus 5 uh, and x plus 1, like this has to be, this, it's not that this has to be greater than 0, it's that it has to not equal 0, right? So this cannot equal 0. In other words, we want to find out what values of x would make this equal 0. So pretend it equals 0 and find out what those values would be, right? Zero product property here, x could be -5 or x could be -1. Either of these two values will make this thing screw up. We'd be a divide by 0 situation. And so we would say then that the domain, we can do this a couple different ways. We can say that the domain is everything from -infinity to -5, not including -5, -5 to -1, not including -1, -1 to infinity. That's one way we can represent the domain. Another way would be something like this in set notation, the set of all x values such that x cannot equal -1 or -5. Okay, like something like that. Again, ask your teacher what the preferred method is, read the instructions for a certain problem. In this class, we're primarily going to be looking at interval notation to express domain, but in some cases where we have a lot of domain restrictions, it's not going to be super practical to use interval notation because it requires a lot of writing. Okay, so I mentioned that the range can be really hard to find, and let's pretend we didn't have, well, let's pretend we didn't have Desmos or something like that available, and we didn't know how to graph this function here. F of x is equal to 3 divided by 2x minus 5. First of all, it's easy for us to find the domain of this function because 2x minus 5 cannot equal 0, right? So that means that 2x cannot equal 5 and x cannot equal 5 halves. So it's all real numbers except for 5 halves is a domain. Always easy to find the domain. The range, on the other hand, is a little tricky. And here's kind of a strategy that sort of is the thought process that we take for even very complicated problems. It's just not always easy or convenient to apply this thought process. And this is what we think about. If I had a really big positive number for x, what would happen to f of x? So for example, let's say x was equal to 10,000. Okay, that's a big positive number. It's not that big really, but it's large. Okay, this would be 3 divided by 2 times 10,000 minus 5. So it would be 3 divided by 20,000 minus 5, 19,995, right? Now, this is a small number. It was, as far as its relation to 0, it's very close to 0. It's like you could pretend it's like 1 over 20,000. It's pretty close to that, right? So this is a 0. It's like 0.000001 or something. The higher I make this number, like the greater it gets. So if it was like, you know, whatever that is, 10 million now, then I would have an even smaller number. Okay. Now, what if x was a big negative number? So like x was equal to negative 10 billion, right? Well, then we would have f of negative 10 billion. Look at these zeros. Trace comas. Okay, I didn't even write that right. I don't think I did. Okay, 3 divided by 2 times negative 10 billion minus 5. This is like 0. Okay, it's like a number that is negative 0. It's like it's negative, but it's basically 0. And so then what number can't come out here? Like no matter how big negative I got or how big positive I got a number that was basically 0 but not quite. Again, basically 0 but not quite. So 0 can't come out of this function. So we would say that the range of this function is the set of all y values such that y cannot equal 0. Or it's negative infinity to 0, not including 0, to infinity. And that's kind of, seems kind of maybe easy or I don't know if this is complicated or easy to you, but this is really kind of a really important thing to think about. Like what happens when you plug in really big numbers or really small numbers, and thinking about that, because that idea is very important. Anyway, moving on. Uh, what's this? If your first thought about what this is it some kind of annoying thing that math teachers do to just make your life more difficult? I mean, yes, but also like this is what's called a piecewise function. Okay, it's called a piecewise function. It basically, all this is it's a function where one type of thing is happening for some part of the domain, and then another type of thing is happening for the rest of the domain. Or you could have multiple, you could have more than two different pieces of the piecewise function. You could have like many of them. So different things are happening throughout the domain of the function. Now it might seem like, again, this is just an annoying thing math teachers give you to make your life difficult. But really, this is a super relevant to stuff like business when you have profits, when you like, or even when you're buying something. So if you're in a company, if you're working for a company later and you have to buy some part or something, you'll find that manufacturers of parts will give you discounts based on your how many you order. So maybe up to the first 100 units, the price is a certain amount. But then from 100, the next like 900 units, from 100 to 1,000, you actually pay less per unit. And then you can imagine then that there's a piecewise function that gets set up over the range of possible number of products you could buy, where you might be able to somehow optimize like your purchase, like get the best value for your money. So anyway, let's look at an example of a piecewise function. Well, this is one obviously, but here's another one. So if I wanted to evaluate a piecewise function, this is really pretty easy. The first thing we need to do is look at the number we want to evaluate. So this one is 6. So we go and we look at 6 and we're like, okay, this function is a line with a slope of 1 and a y-intercept of 2 for values of x that are less than -4. For values of x that are between -4 and +6, including both of those numbers, we have a line with a slope of -1/3 that goes through the origin, or would. Well, actually does in this case. And for for values of x that are greater than 6, we have a different line. If we sketch this real quick, and I'm going to do a very bad job of sketching this, but for values of x that are, like say that's -4, and this is 6, for values of x that are greater than -4, we have something that would look like a line. It's going to want to cross it. So it's doing something like this. We'd have an open circle right there because it's not -4. Then we'd have a slope of -1/3, so it'd be something like this. Oop, that was supposed to be a straight line, but it didn't quite work. That's a closed circle and a closed circle. And then for 2x minus, so for x we have something like, I don't know, this is going to be hard for me to draw, but probably something like this. Okay, so that's what this piecewise function looks like. Now this is still a function. It passes the vertical line test. If you drew a vertical line across the domain of this, you'd only ever hit something once. That means it's a function. So what do we do? Well, we look at the 6 and we say, okay, where does the 6 fall in each of these domain sets of the domain? So it's in this one, right? Because it's in the or equal to 6. So h of 6, we're going to plug it into this one. So -1/3 times 6, 6 is -2. Same thing for -6. -6 is in the top one, so it's going to be -6 plus 2, or -6 plus 2, which is -4. 3 is in the middle one also, right? So it's going to be -1/3 times 3, so this is -1. And then 10 is in the bottom one, right? So 2 times 10 minus 4 equals 16. So evaluating a piecewise function is not really more complicated than evaluating any function. It's just you got to go look at the domain. You got to look at these little domain sections and plug it in that way. Let's look at one example really quick of a piecewise function word problem type thing here. All right, we have Grace is competing in a 15.5-mile triathlon. She swims for 0.5 miles in 30 minutes, bikes 12 miles an hour, and runs 3 miles in 30 minutes. Okay, we're going to need to make a graph here. So set up our graph, label our axis. This is going to be time in, we'll do this in minutes. Okay, and then we're going to have distance in miles. Okay, so it's a 15.5-mile triathlon. So let's say this is 15. If that's 15, then I should have made it 10 probably. That's 10, and that's 5. Okay, and then in minutes we go 30 minutes, an hour, and 30 minutes. We get 2 hours. It takes her 2 hours to do this. So we have 30, 60, 90, 120 minutes. Okay, so if we wanted to sketch what's happening here, first of all, she starts at a distance of 0, and after 30 minutes, she's gone 0.5 miles. So something like she's right here. Okay, now after 0.5 miles, she's going to be going, I don't know why this keeps happening, sorry, she's going to be going 12 more miles. So from 0.5 to 12.5. So let's say that's 11, 12.5. So she's going to be going up to like this area. And that's going to take her an hour. So an hour later, she's at 90. So something like this. Okay, and then the last leg of the triathlon is a run, where she runs the remaining 3 miles to the end, which we'll say is like up here, and she does that in the remaining 30 minutes. So something like this. So what we have then for her graph, her like distance versus time, is she's swimming, she gets on the bike and goes much faster, right? The slope of a line on a distance versus time graph represents the speed, and then she slows down for her run. You can't really quite run as fast as you can ride your bike. So this is what we're looking at. Now, if we wanted to write a piecewise function to represent this, well, all we have to do is say, okay, Grace's distance as a function of time is equal to these different things. So first of all, she had this line, right? This is a line. The slope of this line is, if we do it in minute and miles per minute, which is a weird unit, but that's what we're going to go with, is she's gone in 30, her rise over run, right? Her 0.5 miles in 30 minutes. Okay, so maybe 1/60th. So 1/60th t. That's that part of that part of her triathlon looks like that, and that's only for values of t that are less than 30 minutes. Okay, then what's next? Well, now she's got this. What's the rise over run of this? So the rise was, she did 12 miles and she did it in 60 minutes, right? So 1/5, that's the rise over the run, the 12 over 60. 1/5 t, but then where would that cross the y-axis to get like the y equals mx plus b? How about this? I don't care. What's this point? This is 0.5 comma 30, right? All right, so y equals, remember what the equation of a line is, y minus y1 equals m times x minus x1. So y minus 30 equals the slope, which we said was 1/5, times x minus 0.5. So why don't you just add 30? So y is equal to 1/5 x minus 0.5 plus 30. So what is that? Wait, does that make sense? 30 minus y1. Yeah, that's fine. So this one would be then, wait, this doesn't make sense, does it? 1/5 x, you have one, should it be plus 30? Oop, I did this is backwards, I'm sorry. This should be 30 and 0.5. I was mistaken. So 0.5 and 30, 0.5, 30, and 30, and 0.5. So we're going to have here 1/5 t minus 20 plus 0.5, and that'll be for values of t that are between 30 and 90, right? And then finally, what's the rise over run of this? Well, this one, she went 3 miles in 30 minutes, so 1/10. This would be 1/10. And if we do the same thing where we figure out the points, like this is another point, or even let's say this point. This point is she's gone 120 minutes, 15.5 miles. So if I plug that into this equation, I'll have y minus 15.5 equals 1/10 times x plus, minus 120. So y will equal 1/10 times x minus 120 plus 15.5. So we write that, but it's t, right? But minus 120 plus 15.5, and this is for values of t that are greater than 90, but greater than 90, but less than 120, because she ends at 120. Anyway, it's a little bit complicated, but now if you wanted to know where she was at any point at any time during this race, you could just figure out where she at t equals 45. At 45 minutes, wherever she be, go right, 45 is in this one, plug it in right here, and you'll have her distance after that amount of time. Anyway, this is just modeling using piecewise functions, but we've talked a lot. This has been a 35-minute video, oh my goodness, all about properties of functions and the idea of a function. Hopefully that was helpful.